Hello everybody. So today I'll be presenting a demo for network defense artificial intelligence. This demo is actually suited for those in network engineering, IT or cybersecurity niche. Regardless, if you're in any other domain, it doesn't mean you would not benefit, but it's just native to those in the specific domains I mentioned. As well as those in artificial intelligence space, you will definitely follow along, specifically in the reinforcement learning niche of artificial intelligence. Actually, they're the ones that would really understand, or that this demo is more native to. But every other person can follow along. It's very interesting. I might be biased to it because this is where I enjoy spending my time, right? Network engineering, cybersecurity, AI. So I might be biased, but I hope you would enjoy it too. Anyways, let's have a quick overview. This particular engine that was created in this project is a unified engine that contains both the competitive and the cooperative engine. What do I mean by competitive and cooperative in AI cybersecurity landscape? So, from a competitive aspect, just think of this as an attacker trying to break into an organization, right? The organization typically would have the defense or blue team that are working round the clock to stop the attackers from actually infiltrating the network. So that's where the competitive is, right? So this we are talking about a zero-sum adversarial game. So the competitive is an external attacker trying to hack into an organization, and the organization is trying to prevent the attacker or react if a breach has actually occurred. From a competitive view or lens, we are talking about an organization that contains both the attacker and the defender in under one umbrella, right? So typically enterprise organizations have the red team that their job is to always try to like find vulnerabilities within scope, and the blue team slash defense is always going to try to like mitigate them, right? So that's to it's kind of like a battle readiness kind of approach. So the organization knows what to do in case those scenario actually plays out in the competitive landscape. So yeah, this engine actually has both, as you can see. You if you want to train this model, you will just switch this from competitive to the cooperative, so, right, or vice versa. And we can see we have a dynamic environment spin up. So if it's competitive, we are going to have 10 environments or 10 parallel environments spinning up, and if it is cooperative, we're going to have 20 parallel environments spin up. And obviously this is the directory where um, all the goods are actually being saved. Again, to check whether it has GPU, which is definitely preferred for the time it takes to actually train these particular models or AI models generally. One thing that would interest us here again, for those in the reinforcement learning domain, we can see some of the hyperparameters that we have in here for tuning, as well as the neural network topology. We have a small one here because as we here we have only two. We have only about that's two, three, six, nine different hosts against one, two, three, four, five, against five different networks, right? So it's not a very large network topology. So the neural network is is not as large, right? So this is a quick test run. For the hyperparameters, we can see for those in like the reinforcement learning, we can see we have the um, buffer max length, batch size, the gamma, all sets, and for the total episodes, we have 6,000 here for competitive, or we can put 7,000 for cooperative. So again, it depends. It depends on the training method that we are trying to do. So anybody that wants to train the model, if you put it in competitive, you this is just a personal preference, but I would prefer people to use 6,000. And if you are in cooperative mode, if you change this to cooperative mode, you can put 7,000. But again, there nothing here is set in stone, right? The environment also here can change, right? Those are like the, I would say, the changeables that are not like very very static, right? We can change whether it's competitive, we can change the number of environments, and then we can change the total episodes depending on how long we want the model to actually train for. So as discussed, we have the network topology. This network topology is divided into 5 different zones. So we have the public DMZ, the DNS services, we have the corporate, the Active Directory, and the secure core. So each of these, again, we know that when the most vulnerable entry point is usually the public DMZ, because that's where um, that's the ingress into our network by the whole world, right? So this is typically the most vulnerable, and that's why we have this marked with 0. 0.7. And as you can see, very high vulnerability is 1.0 here, and the lowest here is 0. 0.1, which is our secure core, because again the secure core is connected to the Active Directory, and that is an external, or that is that is a point of entry regardless of how secure this is. So that's why we don't have a 0. 0.0 secure score, right? Except you are living under a rock, that's when you can have a 0. 0.0, but so far it's connected, you cannot have a 0. 0.0. The base vulnerability score is being put through the MITRE attack framework. So we have the MITRE attack framework here. That's what we use to get this vulnerability scoring. And from the number of hosts here, also this is also very very configurable, right? Together with like the number of environments. The number of hosts is also very configurable depending on how large um, the amount of hosts reside on the network, right? So it can be from 200 to 2000. Again, that's a limitation on like the enterprise structure. For the number of environments here, I should mention that the number of environments here, theoretically, it has no limit, but it is actually hard coded based on the underlying GPU infrastructure, right, as well as the RAM and processor and all that, right? So that's the hard limit for the number of environments that we can spin up, but theoretically, it doesn't have any limit. One thing before we move further here to know is with the network topology, right, we can actually, instead of creating this manually, because it's going to be, especially in like in large networks, it's going to be very hard to design the network and the amount of hosts, right? So a better approach would be to use a dynamic network topology generation that transforms the network topology into graph-based RL environments. What do I mean by that? Here is an example. So this is for those in the network engineering space. We know this is how a network topology is typically going to look like, right? But in the reinforcement learning world, the agents do not understand this. So what we have to do is we would have to transform this into a graph-based RL environment, which reinforcement learning agents actually understand. So the typical network topology is going to be transformed into that, and that is what is going to allow the agents discover the network and hack and defend and understand how the network is, right? To be able to take in all those policies. So yeah, that's a very very cool stuff. So that's where we have. That's why I have this saying that like this would be integrated with network observation tools. I'm pretty sure. I don't think I know any tool currently capable of doing that, but definitely folks will be working on that, and especially in the tech space, right? For mapping network topology into graph-based RL environments. This graph-based RL environment is what again is typically used. Just a quick introduction is it is typically used by like social media, right? Or I would say recommendation engines within social media. That is what is being used to I would say to graphically map the user accounts or to connect the user accounts with I don't know with similar like say friends or similar interests, right? Like it's all, so that's where the graph based environment kind of reside. But network engineering also use that approach that like social media engines kind of use, right? From the reinforcement learning perspective. Yeah, so that's a quick introduction into the configuration. The other aspects I'm not going to really display right now, maybe in subsequent videos, but this is to just show the trained agent in action, right? Like the agent has been trained. If we move in here, um, if we move to our document and we actually go to like defense, this is the competitive, it's been trained. We can see the checkpoint here has been trained. We have about 400 MB of like training data sets. We have the logs here and all the cool stuff, right? So also if we go to cooperative, we have the same thing here. We can expand the checkpoints. So these are all the training data sets that reside for the agents. You can check the properties and we can see this is about 500 and something again, because this is 6,000, this is 7,000, right? So this is definitely has more content than the competitive. So just so we dive in here, we can see all the good stuff, all the checkpoints, and all the data set that resides for the competitive agents also, right? So um, this has been trained, and we would see that later also using TensorBoard analytics platform. Um, what else? What else? What else? So let's actually then look at this trade agent, right? Like so we've trained this agent, the agent is ready to go. One thing I think we should actually know here is we would notice the human and ghost visualization. I want to point out that the human visualization is going to be more robust as it contains more information regarding what's going on when we actually run the program, while the ghost visualization just gives us a quick summary into what's going on. Well, you might ask, why are we having those two? The ghost visualization is for if you want to run, say, I don't know, thousands of simulated episodes. Ghost visualization is good, right? So it doesn't consume a lot of memory and GPU usage. But if we want to see more in-depth detail into what's going on, we will definitely use the human visualization. So without much theoretical work, let's actually dive into what's going on. But first, let's look at how we are doing with time. So we have about 15 minutes, so that's cool. So again, now let's start this. The first thing we would notice immediately, right? Let's make this, because it's going to ask us which mode do we want to run in. So do we want to run in cooperative mode, or we want to run in competitive mode? Again, I already explained this. Cooperative, both agents are competing, but they have a shared overarching goal, right? So that's the cooperative. While for the competitive, it's more of an adversarial zero sum results between the blue team and the red team. In the cooperative mode, it's kind of they have opposing goals, but at the same time they have an overarching cooperative goal. So when it asks, let's hit one for cooperative. It checks for the directory that I just showed, and it checks these two directories and sees that. So it asks us how many trials do we want to do, right? So if we want to do, like, say 6,000, so the best approach to use at this point in time would be the ghost visualization. But since we are just running 6, we can do both. So let's do 6. Then it asks us which mode do we want, right? Which is ghost mode or human mode, right? Again, I already explained that. Ghost mode is fast evaluation quickly, while the human mode is a real-time frame dashboard rendering. So let's start with the ghost mode. We hit one. It will ask us what do we want to use from the checkpoint perspective. For the cooperative, is best we use um, the best overall error score, right? And I already kind of highlighted this is the best for cooperative. So I'm pretty sure you'll be wondering what's like the difference. So when we are talking about the best overall error score, what we are talking about here is we are selecting the best error whereby the red agent and the blue agent have actually coexisted. They've had enough time to mature, right? So red is at its peak, the red agent is at its peak performance, and blue agent also is at its technically its peak performance too, right? So both of them are giving like um, equal time to actually figure this out, right? Like, and we are selecting where both of them actually had their best performance, and we are running this against it. The latest available checkpoint is just use the the, the final training data set, right? That's what the latest available checkpoint is there for, to use the final training data set. While the best defensive error, which is what we would use for competitive, that one actually is for selecting the error whereby the blue agent was at its strongest, right? So that's what we would use for competitive, where the blue agent was at its strongest, not when it has co-evolved with the red, right? But this is where blue is at its strongest, because at this point in time the defensive agent is defending against an adversary, right? So you need the defensive agent to be at its strongest during this particular era. Or while for the cooperative, right, like this is the internal complaint running this, so we want both of them to be at their strongest. So yeah, that explains kind of the best overall defensive error and the latest available checkpoint. So it has been highlighted already which one is best for whichever mode, but it doesn't mean like you can't play with choosing a different error. But for this demo, we would be using what's best, right? So once we hit one, uh, then we start the training in cooperative mode, and immediately here we can see that for the six different trials that we had, defense was actually victorious. The first one, the attacker was evicted. The second one, um, attacker could not do anything because the network was hardened. So regardless of what attacker was doing, it was kind of pointless because the network and host were already kind of hardened. From the third one also, we can see the attacker was evicted, and we can see the attacker made 11.1% progress, right? So before the defense knew what the attacker was doing and evicted the attacker out. For the fourth match here, we can see the attacker could not do anything because the network was also already hardened. While for the fifth one, the attacker was evicted, but the attacker actually didn't make any significant progress. That means the defense caught the attacker pretty much early into the attack queue chain. And finally, on the sixth one, we can see here that the attacker made 11.1% progress, but the defense kind of evicted the attacker out. To a quick summary, we can also see like there were six different matches, and it was a completion rate by the blue team of 100%. So for 4 out of 6, the blue evicted the red team, and for 2 out of 6, the red team could not actually do anything because the network was already hardened, right? So this is the ghost mode view, right? You can see out of those 6 trials that we had now, the defense was fully victorious in all 6. So now let's actually look at this mode again in human view this time, and it also gives us kind of another test run into like the red and blue agents um, battling it out, right? So they will battle it out again. So let's do this one more time, and this time we have cooperative also, right? It checks the logs, everything is good. How many do we want to run? Let's say 6, and then we hit 2 for human mode, and it tells us, it asks us, okay, yeah, we still want to do the best defense, the best overall error score. And when we hit this, notice here the overall error score here is episode 6000, right? I'm pretty sure that would have been similar if we had gone up here. It's similar to, so this is episode 6000, so 6000 is the best error. So out of like for the competitive, right, like error 6000 over 7000 is where both agents actually were at their peak performance. So let's take a look, and immediately here we can see already that this one has more details than like the ghost view. So we have this broken down, we have the total number of nodes, which includes the network and the endpoints or the hosts, right? So the network and the hosts here, we have about 13. You can see here that none here was fully compromised, right? Like no no breach or compromise occurred in the whole network. We can see here immediately like this had zero breach progress. The network was hardened 9/9 hosts. All the hosts were actually hardened already. So defense was victorious, right? An attacker could not do anything because the network is hardened already. And as you can see here, the network is actually hardened, and there's really nothing the attacker could actually do. If we check the second trial or episode, we can see we triggered an eviction. Although the network was fully hardened, because the network was fully hardened, maybe the attacker just noticed, the defense noticed the attack throwing some reconnaissance, and still, went ahead to stop that little movement that was occurring. So we can see here defense is victorious, and the attacker was actually evicted here. Also here we can see an eviction was triggered here. Again, defense evicted the attacker. The hosts, 6/9 of them were hardened, but there was no breach progress from the attacker here. Same with these, all hosts were hardened, and nothing that attack the attack guys could actually do. So the attackers were inactive due to hardened network already in this particular one, or in that particular match. Here we have some activity here. There was a breach progress for about 11.1 percent, but overall nothing was fully compromised, and defense evicted the attacker. Defense hardened 6/9 hosts, and for this final one here, we can also see there was a breach progress of 11.1. Also, no fully compromised node here, and defense was victorious due to the attacker being evicted. And we can see a quick summary of these six episode or matches that we had. Defense triggered for eviction, right? And for two of the wins, it was due to inactivity because the red could not just find any breakthrough. There was nothing the red could do. So again, this is 100% win rate for the defense team. So yeah, that's an awesome view, right, from both the ghost and the human view for the cooperative, right? So the cooperative, and one thing I should mention here is, here we have a mean joint score, all right, because it's cooperative. Regardless, it's cooperative, and the progress, mean team progress, right? Everything is a team. It's a team sport at this point in time, right? The red and the blue are in the same team. So there is no overarching kind of winner loser situation, but that's from the cooperative. But the evaluation of each individual agent shows that, like, the blue definitely won a lot with 59.9% score, and the red had a negative 2.04. But in the cooperative outcome, it doesn't really matter because we are looking at the overarching score, which means like it's 28.93. So that's all for cooperative. Now let's look at the competitive mode. So let's clear this, and we will do the same thing, but now we would be looking at the competitive mode. We would hit number 2 for competitive, and then let's do 7 for 7 trials here, and then hit this. It asks us the same thing that we are already familiar with. Ghost mode, And here we can see it's the recommended here has changed now to like best defensive error, which is number 2, and then hit number 2, and immediately here we can see it's the best defensive error is episode is like the 1000 error, right? For the cooperative it's the 6000 error. Also here we can also see from the 7 different matches that the blue team won all 7. Attacker was evicted 1, 2, 3, 4, 5, 6 times, and there was inactivity in 1 time here. We can look at the reward here because it's competitive. Immediately here we can see the total loss here for the red is the total gain for the blue, and it's definitely true if it's vice versa. If red is winning, it will be total loss for blue and total win for red. But in this case, defense is victorious, so defense takes all, right? So that's how we can see this. We can then run this one more time, but this time we would be looking at competitive also, 7, but this time let's look at this in human mode, and it will ask us the same thing, best defensive error, and then we wait and let them battle it out. I should be done, I guess. Yeah. And we can start immediately here and see that again no node was compromised. By node we mean the network as well as the host, right? So none was fully compromised. But here in the competitive mode, 11% progress by the red team occurred, or by the adversary kind of occurred, but the defense triggered an eviction. We can see the second episode, and here we have some good activity here too, because the bridge or the offense team kind of progressed with like 22%, but was evicted by the defense team. And we can see here that like network hardened 5/9 hosts. Here attacker was inactive because again we can see here this is fully hardened, so the eviction signal here is clear because there was nothing to do. The attacker could not just find a way through. Here we have 11% too, but defense triggered an eviction. We can also see the hardened network is 7/9 here. We can see here defense was victorious, but here defense hardened only 2/9 networks, or 2/9 hosts, but prevented, but was proactive, right, in any attack sequence that was coming, because there was no breach progress, although defense actually only hardened 2/9 hosts, but there was no breach activity, no breach progress activity possible. So the blue was very, very watchful in that particular scenario. Here, fully hardened network, and defense wins because the attack can't do anything due to hardened network. Also here, we hardened this in 3/9 hosts, but there was no actual like hacking progress possible because the blue team was very proactive, right? And yeah, we can see the evaluation here. Also here we can see it's fully adversarial, in the sense that red's total loss is blue's total gain, right, from this competitive mode. And as discussed, the competitive mode is like is fully adversarial. So this is when an attacker is trying to break into an organization, right, as opposed to the other aspect of it. So this gives us a quick overview into what's going on behind the hood and or under the hood for this particular like defense model. Um, One thing I would like us to also see before we call this um, a close is to look at the tensor flow for cooperative, and let's hit the same thing for competitive, right? And now that we've done that, let's actually open the link, and then let's hit this and let's open the link for competitive. So right here we can see the tensor board. Again, I'm using TensorFlow for this particular training. So using the analytics, or I'll say the visualization platform, which is TensorBoard. And scrolling to the rewards, you can see the amount of training episodes. We had 7,000, right? So the way to calculate how many trials kind of happened is we would take this 7,000, then we would multiply that 7,000 by the number of environments. So depending on which mode we are, right? So I can see this is 7,000. 7,000, as we can see here, is we have this is for cooperative mode. So we will take 7,000 cooperative mode times 20, because number of environments, and the total number of steps per episode, that will give us our total time step. All right, so times 20, 48. I don't know, someone can do the math. Let's actually do that actually. So that would be, let's open a quick calculator. So that would be 20 times 2048 times 7,000. So this gives us about is it 200? Yeah, 286,720 time steps, right? Like that was taken for the cooperative, while for the competitive, I think, as we can see here, I don't know, that would be 10 times 2048 times 6,000. So that's about 122,880,000, right? So that's how you do a quick calculation for the time steps. Um, but yeah, back to this, we can see the agents here. We can see the blue agent and the red agent's reward. The value here, because again it's cooperative, this is 59.9, and or the total one is 58.7, while the total one here is negative 15.41, right? So that's to show you that it's cooperative, right? Like, so that's their individual rewards based on them achieving their goals. We can see the loss. We can see blue's loss is in 0, so that's a very good loss ratio. Red is definitely not doing well because it's not hitting its goal, while the overall while the loss entropy here is also very very good in 2 point, you can see the graph falls around like 2.8 to 3.2. The regularization loss is awesome, so this is in 0, so that's the mistakes, I guess, right? So that's super awesome. um, for the learning rate, you can see it's reducing over time to prevent policy decay. The way I did it is I ensured both learning rates on both the blue and the red agents are decaying at the same time. I think I have that somewhere here. Their decay rate is like the same thing. We have the same 1e minus 4, and then we have an exponential decay rate here that's that goes down by 0.96 for both red and red and blue agents every 1000 steps, right? So the decay rates for both agents actually reduced together, right, to ensure it's a fair competition, not ensuring one of them's rate is decaying and the other is still stagnant. Both have to decay simultaneously to ensure like the agent is fully balanced, right? So again, you can play with it, but I would say this is like the best way to leave it um, to ensure a balanced and equal training data set, right? We can also see some of like the hardware details, the GPU utilization, the temperature, the RAM usage, and all the cool stuff, right? So this is for the cooperative agent. For the competitive agent, which is like the winner takes all, right? We can also see the hardware details here, from also the temperature usage. We can see the RAM usage, the CPU percentage usage, also the learning rates for both agents are actually the same to ensure like it's fair. And we can see the loss here from the competitive is actually very very good, because again, this is, we are not sharing. If we look at this, it's, there's a bit more symmetry here, or you can't see this because again they are kind of sharing they have an overarching sharing goal. So this is always going, because blue is stronger, this is always going to be kind of different as opposed to or the loss oh no, I'm looking at the blue loss. Okay, we are not pulling that. Okay, yeah, this is what I was looking at. Yeah, so the blue loss here is stronger because again we are in a shared goal, similar to how the reward structure works. We would have to kind of it's not symmetric, right? Like, or a zero sum kind of thing. That's why it's kind of looking like this. But in this other way, it's very similar because now both of them have to perform at their optimal, right? Because both of them want to um, defeat each other. If you want to look at it in that case. So here we can see this is also like a perfect working model. We can also see all the losses because again this is individual. We are not sharing or we are not grouping everything as one, right? That's why we can kind of see like from the rewards the to the total blue loss and red loss, it's all kind of patched up. It's not like as individualistic as the competitive mode, right? So yeah, so this is more like I would say collective in a way, right? This is more individualistic. And then we will look at the rewards here. You can see this here, total gain here is total loss here, right? Also, it's the same principle, but you can also see here the learning rate is similar. They both kind of reduce over time, and that's like a good best practice to prevent policy decay. Or another way to kind of do this is in between training, you kind of stop it, you make your adjustments, and you continue the training, you stop it, or you can just kind of do an exponential decay gradually that goes with time, which is what has been implemented here. Yeah, that's about the I would say the visualization slash analytic perspective of this. Uh, and yeah, that's super cool. So a quick overview again. The human view here, why I like it is because it gives us the analytics also, right? The agent analytics into what's going on, while the ghost view is for like running batch or large number of like training, right? So you don't flood, so you don't exhaust your GPU as well as memory, right? Like this is when this is always going to be very very useful. But at the end of the day, they both do the same thing. You can see the final results, whether the attacker won or the defense kind of won, right? The major difference is how we can actually see this information. That's like the major difference. I think that's about all. One final thing I just want us to just check is just more on the software side, as opposed to like the AI side. So if we see here, we have defense here. If we rename this defense to 1, 2, 3, so this is competitive. If we rename this to competitive, and then run this, right? Because now we have competitive 1, 2, 3. Oh no, we are not there. Run this as competitive, right? And say we want competitive. It tells us obviously because the directory is not there, but it then tells us that okay, we can select cooperative, right? Because it can see that there's cooperative, so cooperative exists, but competitive does not exist. So it's saying, hey, we can train the agent. If we can train the agent to actually possess the competitive mode, or we can run what is available right now, which is cooperative mode. If we go back here and rename it back to competitive, and run it, and we hit competitive, right? Again, now it can see the logs and all the things required, all the directories required to actually run the particular to start the particular match. So let's exit here and clear, and let's why not, let's do the same for cooperative, because I mean it's so good we have to do it twice, right? So why not? Let's hit that for cooperative, and if we hit this and hit cooperative, we're gonna get the same error, right? Like um, that we should train the agent in cooperative, but it tells us that hey, competitive exists, right? So the competitive exists, but cooperative does not. So we should train the agent in cooperative to be able to run that particular mode. So let's revert that back to cooperative, and then if we run this, everything looks good and we hit cooperative. Now it can see the directory and all is good. So and then the agent can go start doing its thing. Yeah, so that's about all what I wanted to share with everybody regarding this um, unified symmetrical competitive and cooperative engine, right? It's a unified engine, so it's a two-in-one engine, so that's super awesome. I love this project, and I was very excited to share it with everyone. So yeah, feel free to enjoy and check out the open version that has been released. The open version is currently on Hugging Face. You can see this the competitive mode released on Hugging Face as well. You can either pick it from here or feel free to pick it from here also, right? Either or is perfect, right? But again, responsible use, please, because the agent um, can be a rogue agent in the wild. So full responsible use and for research and educational purpose only, not for hacking into or trying to hack into any organization. Anyways, thank you all for watching, and have a great day.